Good evening, everyone. I'm Anish Ambekar, PhD candidate from ISC Bangalore. Welcome to this week's live session for the NPTEL course, Computational Mathematics with SageMath. As is the custom every week, we'll be going through a few examples through which we'll be further elucidating the concepts that have been taught in this course in the current week. So the first example that we have is on asks us to use second method to find the real root of the following equations. We have been given two equations. The first equation is log of x plus x minus 3 going to 0. So we'll first define the equation as an expression f of x. Before that, we'll be specifying the variable x just to keep up with the nice practice that we have. F of x is equals log of x plus x minus 3. If I just show f, it will show me the map x going to x plus log x minus 3. To get an idea of where root may lie, we'll first plot f of x over a sufficiently wide range. Since there is a term including log of x, we know that x must be strictly positive for this function to exist. So if I run this, if I plot the function, I see a root lying somewhere between 2 and 4, and it seems that the function is monotonously increasing. It's quite straightforward to think of it as so, because as x increases, both log x and x increase, making this whole term go up. So there will be only one root, and we have to find that root. We know now that it lies somewhere around between 2 and I think this is 2.5. A quick recap of the secant method. It's an iterative method, a numerical method to get an approximate root, and it functions by calculating. It's an unbounded method which calculates the root, or rather the next iteration of the root, sorry, next iteration of the guess of the root as a function of the previous iteration, previous two iterations rather. So xk plus 1 equals xk minus f of xk into xk minus xk minus 1 upon f of xk minus f of xk minus 1. To those of you who might have gone through the lectures, you might see that if xk and xk minus 1 are sufficiently close, this whole term essentially starts to become close to derivative of f of x at xk. And then in that case, the closer they get, this method would start resembling Newton's method. We'll come to that later on. But first we define the second method function. It takes three compulsory arguments. First is the function f. Next is x0 and x1, which are the first two guesses of our root. Maximum iteration and the tolerance limit. X0 and X1 are specified. Our iteration count is set to 0, and our maximum error is specified to be 1, and will only continue if our this error term is keep remains larger than the tolerance, or the iterations are less than maximum number of iterations. Then the next root is basically calculated as x2 is x1 minus this whole expression that we have written here, and it is appended to an array called as root. And while n is less or equal to max iterations and error is greater than tolerance, we run this loop wherein we iteratively calculate, uh, given previous two guesses for the root, we calculate the next possible guess of the root. And this whole thing keeps on happening, and we keep on adding all the roots to all the guesses to this root array. And at each time we also calculate the error based on the previous guess of the root and current guess of the root, and sorry, increase our counter sufficiently. So once this whole thing is done, what we do is, if our If our number of iterations maxes out, then we print that we have not achieved our objective of converged root. Otherwise, we return x2, which is basically the last entry in the root. So if I'll just run this cell, so the function is now specified, and now I'll be running the secant method. So here I'm leaving maximum iterations as 200 and tolerance as 1e minus 12. My first two guesses, I'm just taking them as 1 and 3, not necessarily on the opposite side or same side, just 1 and 3 for the sake of it. And second, this gives me out a sorry, this gives me out the root to be around 2.207. So this whole algorithm is implemented to find this root. Another function that we had been given in the problem is cos of x minus x into e raised to x going to 0. Again, as is good practice, specify the variable x, write down the expression or the function g of x, and just print out how the function map looks like. So the function map goes from x to minus x into e raised to x plus cos of x. So all good. You can also estimate a few things from here. If x is sufficiently large, because cos of x will be bounded between minus 1 to 1, if x is sufficiently large positive number, minus x into e raised to x would dominate and be a large number. So after a while, after some particular x, your function would keep on increasing in the negative direction. So increasing magnitude, but in the negative direction. So if I just plot g of x, this is what I see, right? So it's for the range that we have chosen minus 3 to 2.5, a peculiar range, but if I say take a larger range, you can see that for the larger values it just goes on to negative infinity as we predict. Right? If I limit this to say only 4, seems that we have a few roots here. Okay, if I say do this to 101, this is how I see. So this function has like a lot of roots, and that can be guessed also from the fact that as x goes to negative infinity, e raised to x will go to 0 and cos of x would remain. So finally g of x for sufficiently large negative number would basically be oscillating between minus 1 and 1. Now I'll just go back to the range that I had specified previously. So here is a case where here is a snapshot where I have say two roots. I can see two roots based on these limits of the abscissa x, and I wish to find both of them. So for the first one, I'm just giving for this root, I'm just giving the first two guesses as minus 3 and minus 1, and for the second, for this root, I'm giving the guesses as 0 and 1. If I run this, I get two roots like this. If I have to say do it to minus 10 and 1, I can see that I have more roots here, so I could say find the root between minus 4 and minus 4.25. That gives me this root. So we could calculate like this seems to have like infinite number of roots. We just were asked to find one of those. So this solves this particular problem. Any doubts here? You may ask them now. If not, I'll continue with the second example. Okay, it seems this example was clear. So we'll move to the second example. Here we are told that the following equation pertains to the concentration of a chemical in a completely mixed reactor. So C is given as C1 times 1 minus e raised to minus 0.04t plus 0 C0 times e raised to minus 0.04t. If the initial concentration is C0 equals 4 and the inflow concentration is C1 equals 10, compute the time required for C to be 93% of C1 using Newton's method. So a roundabout way of saying this is concentration varies as a function of time. There is an inflow concentration as well as there seems to be some sort of not sure how to say this, but some sort of leakage, so to speak, or rather not leakage, rather the difference in concentration seems to be adding up to a particular parameter, and together we the concentration we expect the concentration to move up because as t becomes very large, this minus 0.04t becomes a large negative number, and therefore the contribution from e raised to minus 0.04t both in the C1 and C2 term should vanish, finally giving out C2 finally converts to C1, which is 10. So we have been asked to calculate at what time t C becomes 93% of C1 or 9.3. So as is the custom, we first specify the variable t. We also specify our constant C0, C1, 4 and 10 respectively. And then we write our expression. C of t is as given here. I'll just show C. So this is what we get. So this C0 minus C1 clubbed together to form minus 6. And you get 10. Okay. Next term, A and B are A and B are specified as A and B are specified as 0 and 100 as in my limits of time, so to speak. My y0 of t is c0, my y1 of t is c1, and my yt of t is 0.93 times c1. So these basically create my bounds to the concentration, and they will be plotted along with my concentration function c of t for the range t going between a and b. Appropriate colors and labels have been assigned. If I run this cell, you can see that this is my concentration curve and it keeps on increasing, monotonously increasing. This is my initial concentration and this is expected to be my final concentration. Somewhere in between, this green line is my target line, which specifies 93% of C1. So I expect my route to be somewhere around 50-55 mark uh, time. Sorry, 50-50. T equal to 50-55. A quick recap on Newton's method. Uh, it's an iterative method for finding root of a polynomial or a function, and wherein we have the next iteration depending solely on the previous iteration. So xk plus 1 is xk minus f of xk upon f dash of xk. Writing this in function form, we define the Newton's method or Newton-Raphson method as having three compulsory arguments: function, its derivative, initial guess, and two optional arguments: maximum iterations and tolerance. Again, initial guess I equal to 0 is basically my counter, and error refers to my error term. So I run a while loop while I is less or equal to, while my iterations are less than my maximum number of iterations and my tolerance is greater than, and my error is greater than the specified tolerance. I compute the next iteration of my Newton's method, next iteration of the guess for the root using Newton's method as x1 is x0 minus f of x0 upon f dash of x0. Error is basically the absolute of difference between the two guesses, two consecutive guesses, and then I just increase my counter and reassign my guess value. Once this row runs, either due to maximum number of iterations or tolerance, uh, or like reaching within tolerance, I return my root as well as value of the function at that root. So in our case, I define a target function as c of t minus yt of t. I've already specified yt of t to be 0.93 times c1, and then derivative of this function. This function should go to 0, and I calculate its derivative by doing c target dot diff. So we already seen this dot diff in previous classes. We only have one variable, so I'm directly writing dot diff to get the uh, first uh, proper derivative, exact derivative. If I show both of the functions, I see that this is my target function. So this is what should go to 0, and this is my first derivative. Once I run Newton-Raphson method for maximum with my target function, its derivative, and an initial guess, I see this is my I see this to be my solution. So it seems that my solution is uh, 53.71 say seconds, and the error is very small, 2.2 e raised to minus 60. So we can be comfortable that this is the solution that we have obtained. Okay, so this clears this particular example. If you have any doubts so far, you may ask them now. I'll pause it for a moment. Okay, it seems that this was also straightforward to understand. Next example that we have is regarding tells us that the concentration of a pollutant bacteria C in a lake is decreasing according to the equation given here, which is C of T is 70 e raised to minus T plus 25 e raised to minus 0.075 T. Find the time required for the bacteria concentration to be reduced to some, say, 9 using Newton's law. So same process that we have done above, but before going there, you can see that both of these terms are monotonously decreasing, so the functions you should also be monotonous, would also be monotonously decreasing. Then we specify the variable t. We write down the function c of t or concentration of t and just do show t to see how the map looks like from t to concentration at t. So far everything looks in order. Next, we specify, say, the two ends of the, sorry, we specify the ends of the plot that we have as 0 and 20, and we are also plotting the target value y target of t. We have specified it to 9 as mentioned in the problem statement. Now we will plot both concentration of t and the target value with suitable labels. We can see that there seems to be a point somewhere around 13 or 14 where the function matches its target value. If I have to see up more closely, I might also refine this for the plot. So around 13.5, 13.6, I should have an answer. Okay. Next, what do we have? Uh, we have the target function which we wish to drive to 0, which is concentration of t minus y target of t. We are also calculating its first derivative by simply doing c target dot diff, and we'll just print out how both functions look like. So this is what things look like. And finally, I'll be using Newton-Raphson method the function already we have specified in the previous example to calculate what my solution looks like. So the solution looks like 13.622, which also matches what we see, and the error that comes out of after perhaps a lot of iterations is 0. So if I just run this, okay, so 13.62. Yeah, this clears this particular example as well, quite straightforward. Uh, these three examples cover up basically the root finding methods taught in the previous class. Okay, if you have any doubts here, we can stop. Otherwise, I will move on to the next one. Example 4. Create a Sage routine to find the Lagrange interpolating polynomial for a set of given points. So here we have been asked to create a routine, but before going there, as we have seen in the class also, Sage comes inbuilt with a function for Lagrange polynomial. So wherein we have to specify a polynomial ring, so like real numbers with variable x, and within that we can use this function r dot Lagrange polynomials, to which we only have to feed a list of points x0, y0, x1, y1 all the way till x and y. So there are a lot of options depending on what kind of algorithm we should use and how the output looks, we get the output rather. Uh, okay, but here we have been asked to do our own thing. So suppose I choose a set of points. These have been chosen randomly, and I get say like they are not even ordered, as you can see. And if I just print them out on a plot, x comma y plot, I see that the polynomial looks something like this. Right. So any interpolating polynomial will have to go through all these points, and it should, in theory, as is the definition of an interpolating polynomial, wherever or function is specified, it should match that value exactly. At other points, it may not even need to do so. Like it may have some, because you do not have data, it can go through a different nature. So it should match exactly at these points. As you can also see, one of the features of Lagrange polynomial method is it doesn't require the points to be equally spaced along, say, the x-axis here. So even then it can work, and the algorithm is pretty simple, or rather the theory of that is pretty simple. Suppose we have n plus 1 points, xi, yi, I going from 1 to n. Then we write down our nth degree polynomial P1 as L0 y0 plus L1 y1 plus L2 y2 all the way till Ln yn, with the requirement that Li of xj is delta ij, or 0 when I doesn't equal to j and 1 when I equals j. And the way that we have done this is we basically write down it as product of x minus xj upon xi minus xj, with the condition that I should not be equal to j. So this has already been, I think, taught in the class, but I just wanted to mention it here for a brief recap. And so how this works is I have defined my polynomial called as, defined my Lagrange interpolation polynomial function as my Lagrange poly. It takes a single input, points. N is the degree of the polynomial is basically number of points minus 1. We specify the variable x, and we write down polynomial Pn of x as 0 into x, or rather 0 itself. Then for I going from I in the range of n plus 1. So basically here we have 7 points. So n will be 6 and I will move in the range of 7. So I will go from 0 to 6. So this covers all the points. We specify Li of x is equal to 1, xi comma yi is equal to the ith point itself. And then for j also going through all the points, we specify only the xj. Then we check if j doesn't equal y. If j doesn't equal y, then we'll multiply my Li polynomial with x minus xj upon xi minus xj. So basically, one of these terms, each of these terms, one at a time, excluding the term I equal to j. So this will create my polynomial Li, product of uh, product of n terms, and basically each of these li's for each of these I we have one li, and each of these li's will be multiplied with a coefficient yi and will be added to pn. So this whole bunch of theory that we did here is written down here in the form of a function, and then we return the function pn. Let's see what happens here. Pn is my Lagrange polynomial of nodes. Nodes I have already specified above. If I run this, I get a rather big expression. I'll just simplify this because there are a lot of products. I'll simplify this. So this creates, as you can see, 7 points, so 6-degree polynomial. And there is no constant term here. This is because the origin point has been included, which means that basically that y0, y at that origin is 0. So that term is not. So at x equal to 0, y should be equal to 0. So that is also satisfied. So as we see here that there is not a constant term. Now I will plot my function between the range of my nodes. So my nodes go from -5 to +8, and my nodes go from -5 to +8. Since this is an interpolation polynomial, we'll be not concerned with what happens outside of our bracket of interest, and I'll be also plotting the points with it. So as you can see, perfectly uh, overlapping with whatever nodal data that we had as input. So this is my 6-degree Lagrange polynomial emerging out of this. Okay, so yeah, now we have basically constructed our own function for Lagrange interpolation polynomial. Okay, any doubts here so far? Okay, next we have example number 5. Consider the function f of x equaling x into e raised to minus x square. We have been asked to generate 10 points x1 to x10 which are equally spaced between 0 and 1. Define yi is equal to f of xi. Find the Lagrange interpolating polynomial through this 10 points. So 10 points, so you'll have a 9-degree polynomial. We have been also asked to plot both the points as well as the interpolation polynomial. So as is the practice, specify the variable x, specify the function f of x, and check the map. So the map is x going from x into e raised to minus x square. So far, so good. Next, specify the endpoints of our interval. A is 0, b is 1, and we will be plotting f for x going from 0 to 1. This is how the function looks like. And okay, next we have to calculate the nodes or a set of points xi yi for required for Lagrange polynomial. So I specify an empty array called as nodes, total number as 10, and for I going from 1 to n, I calculate xi is a plus b minus a into I by n plus 1, so equally spaced points. Y is nothing but f of xi. Once I print out all those points, one thing that I'm also doing is I'm only limiting the number of digits. Otherwise, if I do not want this, I might also do away with it. So suppose I only want xi yi. This is how I could do it. Right. Next, I'll plot my points. This is how my points look like, and now I'll be calculating my Lagrange polynomial. Okay, so quite a complicated polynomial. If I simplify this, again a lot of things. So this is part of the reason that why I had stuck to few digits instead of the entire thing. So if I now simplify this, so much palatable expression, 9-degree polynomial, and at 0 again you have 0 comma 0, so no constant term. I'll finally plot this. So you can see this equation happening, right? So you have the Lagrange polynomial completely overlapping with your set of points. Here it's important to note that because we are restricting the number of digits to 4, right? This is like a finer point, but there is some sort of noisiness created here at the end of the interval. If I have to say do this again, if I remove this n digits, my expression would become quite large, but my answers would now become more exact. So simplifying, it's still very large. Now if I run this, this is smoothed out, this portion. It may not seem like much in this particular example, but as we'll see in the example below, it can be a bit of a problem when we try to restrict the number of digits associated with uh, our points. Okay, so hopefully this one is also clear. I'll pause for a moment if you have any doubts so far. Okay, next we have example number 6. Here we are told to obtain a polynomial p of x that interpolates f of x equaling x upon 1 plus 25 x square using 21 evenly spaced points. Then for each of these points, find the values of f and p and check where is the largest difference between these points. So 21 evenly spaced points, right? We already sort of expect, because this is an interpolating polynomial, if everything is correct, the interpolation should match the exact function value, especially because this is sorry, the interpolation at specified points should match the exact value, driving the error down to 0. But before we go there, let us see let us see this. Let us specify the function. So variable x, function f of x, and if I show the function map, everything looks all right. My limits I have set arbitrarily to 0 and 1. They may be changed, but if I plot this function between those limits, this is how the function looks like. As you can expect, as x becomes much larger, denominator will grow larger faster and f of x should vanish to 0. Similarly, as x becomes negative, again the same thing should happen, but in the opposite direction. Next, we write down our nodes, set of nodes, so 21 nodes, which means 20 equally spaced, 20 equal sized intervals between 0 and 1. And I write down my x and y as follows. So you can see that I get some values for xi comma yi. I'll print my nodes in on the xy plane. This is how they look like, equally spaced along x-axis. I'll first be using Lagrange interpolation. So I'll be running Pn of x is my Lagrange polynomial of nodes. Okay, a large expression, but we can let it be. Next, we'll be plotting f of x as well as Pn of x as well as the specified point. So we are plotting three things. First, the function, then my interpolation polynomial, then my 20 points, and then my interpolation polynomials between those 21 points. What do we see? You see that there is no uh, there is no there is no f of x visible. That is because it exactly overlaps with p21 of x. If I were to say remove, comment out this, this is what f of x looks like. This is my f of x and p of x overlap, pn of x. Okay, so far so good. Next, we'll be tabulating the error as we have been asked to. So for each row in the table, we'll be writing x comma y exact comma y Lagrange interpolation polynomial and then the error. So if I run this, I already run this, is it? Yeah. You can see that everywhere your y exact matches with y Lagrange interpolation, which is what we expect from a good interpolation algorithm, and the error vanishes to 0. I, I want to demonstrate the earlier point which I have mentioned about number of digits. So I'll just copy this line out here and redo this function once again. If I rerun the function and go through it again, I have a and b, and now instead of an output which looks like this, I get this as my interpolation, these as my points. My interpolation function now looks much nicer. But if I were to plot it, something strange happens. So you can see a lot of noisiness coming out at the ends of my specified points. So were I to adjust my say my x and y points, just remove plot f of x going from point 8 to 1 and point 2 denotes going from 16 onwards. So this is basically we are zooming into the region point 8 to 1 which had a lot of noise. taking a moment. It's a bit dead. Oh, it's just doing that, adding those previous plots as well. Now this should specify only the smaller range on the x-axis. You can see that even though there is noise, it seems like the function does is might be oscillating, but may be reaching close to the points themselves. If I now tabulate the error for this limited number of digits, I see that there is some very small error coming into picture. So we have effectively, by doing this exercise, we are effectively restricting the information that goes into creating an interpolation polynomial, which makes it an entirely different interpolation polynomial, which is very close to our exact function but not matching. And particularly, it has errors at the endpoints, which might be sensitive to the limiting of information that we did. So I'll again go back. I'll make everything as was in the previous case, wherein we had the entire information. So no restriction of digits. And I'll just run through the polynomial as well as the plots. This is have to set it again to a comma b. The entire nodes. Here you can already see that it looks much better, but let us run that. So everything is in line. And if I run again the error, everything vanishes to zero. Okay, so correct amount of information is important. Smoothens out everything nice and easy. And Sage can handle it, so you can let it. Next, uh, another method that we have is spline. It's particularly cubic splines, which matches not only the function values of two adjacent interval at the common point between those two adjacent interval, but the function's slope as well as its second derivative. So if I run a help on spline, I see that it only requires a set of pairs which do not necessarily need to be sorted, and you can say add or delete members from the spine. Sorry, add or delete point pairs from the spline. Okay, and what this does, if I calculate my spline, it just creates this array object. And now if I want to plot the spline as well as my points and the function, I'll be running this and see that once again spline overlaps with the function f of x. If I run the error code again, I get a table which looks like x, y exact, y spline, and you can see that the error is zeroed all the points. So wherever information is specified, we expect our interpolation polynomial to necessarily match that information, whereas in between, we expect it to fill the gaps. So this completes this particular example. So we have also covered like the interpolation part of this week's lecture. Any doubts so far? Uh, it seems this is also clear. Next up, we have an example 7, which says that we have to write a Sage routine to find numerical integral using Simpson's 3 by 8 rule. Hence, use this routine to evaluate the definite integral going from 0 to 1 of e raised to minus x square by 2 by taking n equal to 30. So I think we have already seen Simpson's one-third rule, which approximates interval as with 3 points, which is roughly like a cubic polynomial. Now we'll be going to the 3 by 8 rule, or which roughly approximates a cubic polynomial. So 1 by 3 is for quadratic, sorry, this is for cubic. Suppose we have variable x, my AB limits as 0 and 1, my function f of x. I'll check the map once. So the map looks alright. Next I'll plot the function. So it's like a decreasing function but positive. I'll be calculating, I'll be writing down the Sage routine to calculate this, but to have a fair idea of the answer, I'll be using numerical integral, which is an inbuilt function in Sage, which calculates integral f going from a to b and has, like you can see, a different number of, uh, sorry, which has a number of different uh, arguments, optional arguments. It returns both the function, both the integral value as well as an error estimate, not error, error estimate. So if I run this numerical integral, I get my value to be around 0.855 and then error estimate to be 9.5 e raised to minus 50. So which means that this looks like a decent solution. Simpson's 3 by 8 rule works like this. We approximate integral of f of x dx going from a to b as b minus a by 8, which is nothing but b minus a by 8 times f of a plus 3 times f of 2a plus b by 3 plus f of a plus 2b by 3 plus f of b. So a, b, and the two points at 1 by 3 distance of the interval. So total 4 points, f of a plus h, f of a plus 2h, and f of b. H is basically b minus a by 3, the step size. So we define the Simpson rule 3 by 8. This is directly in the composite form. In the previous class, we had looked at how to define, in the class, we had looked at how to define a numerical integration for one interval and then take it to multiple intervals to create the composite form. I have not written it like this. I am directly writing the composite form, which takes 4 arguments: function f, left hand side limit, right hand side limit b, and number of intervals n. Because there are in this 3 by 8 rule, the step size is defined as follows. So any number of steps won't suffice. We require a number of steps which is exactly divisible by 3. So if that is not the case, we just print out the error and exit. Otherwise, uh, sorry, I think I made a mistake here. Yeah. Otherwise, I write down I calculate my step sizes b minus a by n. So like if there are 6, if n equals 6, my h is b minus a by 6, and then for each of those 5 internal points and 2 points on the boundary, because we have 6 intervals, we have 7 points, 2 on the boundary and 5 in between. I estimate my sum as a summation of a bunch of terms. So the first term, that is f of a, which is left hand side. Next, for I going from 1 to n, if I is divisible by 3, you basically add twice of. So if I is divisible by 3, you can see that this term will be added to itself again, and then the next 2 terms, then the next term, and so on and so forth. So for any term which is divisible by 3 between 1 to n, you add twice of its function value. For all the other terms, you add 3 times of the function value. This will create a large bracketed sum whose sum is basically my sum, and the endpoint at the endpoint again we'll be adding f of p. Then to this my sum, we'll be scaling it down with 3h byte. This creates my Simpson rule 3 byte in the composite form. My function to do so is now ready. I'll be specifying again, going through the process of specifying my limits 0, 1, and number of points as 30. Number of intervals as 30, and then I'll be running this Simpson rule. So my answer is 0.85562, which is what we have also seen. Okay, if I were to say increase it even further, it's already pretty saturated. Not much change, small change here. Just to see how this looks like. Suppose you only have 3 intervals, not 30. We plot the Simpson. We have the Simpson plot. So this should give you an intuition of how we are doing this. Okay, so what we are basically doing is we are plotting the function f. We are plotting the cubic approximate polynomial, or rather the cubic interpolation polynomial based on Lagrange interpolation. So I'm plotting my function, I'm plotting my cubic Lagrange interpolation plot, and I'm also plotting down these lines at like at every one, like 1 by 3, 1 by 3, 1 by 3. So for the cubic part, and then I'm returning this. So this is how it looks like. In this case, it seems like everything looks good, which both of them seem to be overlapping. It may not be clear how things are different. So just to get a feel, suppose I raise it to a very high power, say x raised to 20. Now this is a very sharp function which I doubt can be represented by a cubic polynomial. If I run my, sorry, if I run my Simpson plot function, I can see that this is my cubic interpolation polynomial between the 4 points based on Lagrange interpolation scheme, and this green is my actual function line. So the two areas will not be equal, and that is also, there is also some difference between the two. They are almost same, it seems, in this case also. 0.978 and 0.97. Nice. If I, perhaps I should try to increase this one. The more I increase this, they're still quite matching. Now I think I have to change this and I forgot. So in this case, it's pretty clear by your eye test that you can see that while this area is the white shaded area below the green curve is much larger than the gray shaded area above the green curve. So you expect a 3 interval Simpson 3 byte rule to underestimate your integral value. So it's 0.950 in this case, and 0.995 is the numerical inbuilt integration. So this should give you an intuition of how the Simpson 3 byte rule works and how we have implemented it in our case. Any doubts here? You may ask them now. Okay. Next example, example 8. Evaluate the integral from 1 to e of e raised to x square using Simpson's 1/3 and 3 byte rules by taking n equal to 30. So 30 intervals in both cases, 30 is both divisible by 2 and 3, so should be fine. We specify our variable x, we specify our limits a, b as 1 and e respectively. Function f of x is also specified, and we just check the map once to be sure. We plot the function in the interval that we have. So you basically are raising e raised to e square somewhere. It's a very interesting thing. And now we have to do numerical. Now we check numerical integration. So 323.29. Suppose I have Simpson's 1/3 1 by 3 rule. I am again writing the composite function. So this is taken from the class itself, wherein if the integer of which takes 4 arguments, function f limits a and b and n as the number of intervals. This function only proceeds if the number of intervals is greater than, is divisible by 2. Again the same process, we calculate the composite sums, and you if I is not divisible by 2, you add 4 times f of xi, and if I is divisible by 2, you add twice of f of xi. Endpoints are directly added, f of a and f of b, without a multiplier, and the whole thing is later multiplied with h by 3, and the sum is obtained in numeric form. So I run the equation ab going to 1 and e respectively, n is 30 and 600. So I get uh, a different value, 288.719, which is far quite different from this 323. Next I run the Simpson 3 by 8 rule again, and I get a value of 323.35339. Okay, so the point of this example is to show that Simpson's 3 by 8 rule converges much faster to the actual answer. And you could say, if I have to estimate how many, suppose I require say 60, take 60 iterations. It's going in the other direction. Is it? Suppose I take only 10. This is no overestimating. I think I've made some mistakes somewhere. Okay. For f, for I in the range of 1 to n, this should be here. Right. So I think this is, I made a mistake. Apologies. So this is how the sum looks like. In one case, the answer is 323.29. Simpson's 1 by 3 rule gives 323.31, whereas 323.33. So both of them are very close to the numerical value. Suppose I decrease this to say only 6. This is 331. This is 337. So this is overestimating, that is underestimating. Both of them have some error terms that need to be dealt with. If I increase this to say 600, that's a lot of 323.29518. Okay, right, so we have evaluated this definite integral using both Simpson's 1/3 and 3 by 8 rules. You can, in theory, keep on creating more and more complicated rules based on the form of interpolation polynomial that you choose to have. Okay, so this is what we have for this example. Any doubts, if you have, you may ask them now. Okay, next example, example number 9. Find the largest eigenvalue and corresponding eigenvector of the matrix using the power method. So okay, we'll first specify the matrix A as given here. So we basically get what we have been given. Next, we calculate eigenvalues of A and eigenvectors of A using A dot eigenvalues and A dot eigenvectors, right? We can see that there are three distinct eigenvalues, but four linearly independent vectors. So, which means that if we go to our power method theory that we have been taught, we can see that it requires two conditions, assumes two conditions. Firstly, that this dominant eigenvalue, which is 5, is real and its absolute value is greater than all the other values. So 5 is greater than 3 into A is diagonalizable, or in other words, A has n linearly independent eigenvectors, which is what we see here also. So how, if I have to go through this, I'll be running an import where I calculate the argmax, sorry, from which I get the argmax function from the numpy library, which whose whole deal is to get me the index where my array index at which the value in the array is maximum. I specify an initial vector 1, 2, 3, 4. Doesn't need to be, can be anything. Maximum iterations as 30, tolerance as 0.001, error as 1, and iteration counter as 0. I run a loop. It is a while loop wherein two conditions have to be simultaneously satisfied. First, with the iterations less than maximum number of iterations, and second, that the error exceeds tolerance. If the error becomes less than the tolerance, we'll exit this loop. And how do we calculate the error and so on and so forth? We calculate y as a into x, find out at which value y is, sorry, find out the index at which y is maximum, con, rather convert it, first convert it to, first specify another vector which has all positive values, absolute values of all the entries of the vector, find out the maximum values, so like suppose it's 1, 2, 3, 4, then 4 is the maximum value, and divide this entire vector by 4. This is what the algorithm is for the power method. So the any of these entries, maximum of them is 1. So x1 is y0 by c1. C1 is the maximum of the value in the vector. And then we specify error as norm of x, norm of the difference between current guess and the previous guess, the eigenvector. So we keep on doing this. We print out the iteration number, we print out y, we print out c, and we print out x. All of them are limited with up to 4 digits. So this while loop, I'll run. Oh, max iteration. Oh, I forgot to run this. How it should. So you have iteration 0, 1, 2, and so on and so forth. So y0 is basically a times x0. Then c is maximum of y0, absolute of y0, which is 369. Divide the entire y0 by c value, which becomes 1 minus 5.3 and so on. So this gives us some value and this keeps on happening. Next, for the next iteration, this is the input which is creates y1 from which we get c1 and x2 and so on and so forth. All this happens till so 12, 13 iterations. Once this whole thing is done, at the iteration number 12, we see that between iteration number 11 and 12, we get x12 and x13 respectively, and we see that they are exactly the same. So there's no more changing of eigenvector that is happening in this iterative method, and we can say that our algorithm has converged, power method algorithm has converged. The eigenvalue is 5 and the eigenvector corresponding to this is this value. Just summing this whole thing up into a function, compact function form, so that we can redo this process over and over again when required. Define the power method with the matrix A, initial guess x0, maximum number of iterations and tolerance. And once we find out the final eigenvector, we return that final eigenvector as well as eigenvalue as a Rayleigh coefficient of that eigenvector with respect to the matrix A, which is nothing but x transpose Ax upon x transpose X. If I run this function now for my problem, I get eigenvalue as 5 and eigenvector as 1 minus 0.57, 0.1421. So this roughly looks like 1 minus 4 by 7, 1 by 7 minus 1 by 7 and eigenvalue of 5. If I go back up to compare, I see that for the eigenvalue 5, my eigenvector is 1 minus 4 by 7, 1 by 7 minus 4 by 7. So this matches with whatever value that we have obtained using the power method algorithm. Okay, so any doubts here, you may ask them now. Looks like this is clear. So we'll move on to the next example. Example number 10. Find the largest eigenvalue and corresponding eigenvector of the matrix given here using power method. Again, the same process. Specify the matrix A. We'll print it. Next, we'll print out the eigenvalues of the matrix A, eigenvectors associated with matrix A. So this is how it looks like. Okay, so and I'll just we before I comment on this, I'll just run through the process that we have learned earlier. So I again have my power method function and let us see what happens. So it has given a bunch of stuff that we don't know what to do and how to use it. I could also do one more thing is 0.n digits equals 4 dot n digits equals 4. So it gives me an eigenvalue of minus 0.616 and function like this. So 0.1332, 3 times that, 3 times that, and then 1. So is there a value of minus 0.6166? If I check A dot eigenvalues, that is not there. Indeed, it seems like there are 2 eigenvalues of 1 and then there are 2 eigenvalues which are complex conjugates of each other. So what happened here is basically this violated the assumptions that we had regarding the dominant eigenvalue being a real number and its absolute value being greater than all the other eigenvalues. And then A also has to be diagonalizable, which is not seen. So because it has complex eigenvalues, we do not have, we cannot use the power method that we have been using so far. So this basically, this problem basically shows us the limitation of the method that we have. Next example, find the smallest eigenvalue of A, which is a 3 by 3 matrix given here, and the corresponding eigenvector using inverse power method. So the matrix A is specified. In the inverse power method, we calculate the smallest eigenvalue provided we have, if we can get a suitable guess of the smallest eigenvalue. So how do we have that? At the moment, we don't have that, but we'll go there when the time comes. So first we find out the identity matrix associated with it. It's a 3, since A is 3 by 3, I3 is the identity matrix. And the inverse power method algorithm is as follows. Let sigma be an approximation to the eigenvalue lambda 1, which is the smallest eigenvalue, and sigma be closer to lambda 1 than any other lambda. So sigma is much closer, not even closer, much closer to lambda than to other eigenvalues. Then we invoke the inverse power method. So herein we basically, for the inverse power method to work, we basically have the A minus sigma into ID, inverse of that to satisfy the conditions required for the power. So here we have A minus sigma, right? If we take inverse of this matrix, that is what we are interested in. That is what should give us the inverse. So inverse of this matrix should satisfy the same conditions that were specified with the power method algorithm. So to do so, I'll be running, sorry. For doing so, first we'll assume some initial guess, again 111, maximum iterations, tolerance, and some sigma value. At the moment, I do not know what sigma is. So for this example, I've just taken a small value of 0.01. Next, we specify the matrix ASI as A minus sigma I. And we check if A minus sigma is invertible, then we calculate its inverse. And so this should give us the A minus sigma I matrix that we have here. And then the inverse of A minus sigma I whole inverse. Then we wish to check if its eigenvectors are indeed linearly independent, which is the required condition. Okay, so let us see what all do we have. This is A minus sigma I. A minus sigma is indeed invertible, so invert it. This is the inverted method. Once I get the eigenvectors, these are the eigenvectors in the QQ space. I check the linear independence of inverse of sigma I eigenvectors in the Q3 space. The output is an empty bracket specific, sorry, meaning that inverse of A minus sigma I, its eigenvectors are linearly independent, which is the necessary condition for using the inverse power method. So once this condition has been satisfied, we run it through a loop. Again, the same thing, A minus sigma ID whole inverse into x0. You can see that this expression y0 is A minus sigma ID whole inverse into x0 is similar to y0 is A times x0, which we had written. So that is why the insistence on checking once what happens to uh, inverse of E minus sigma ID. Then we just do the same thing wherein we scale down to 1, print the values and so on so forth. The only exception is that this D1 is sigma plus 1 by C1. X1 is Y0 by C1, so everything is scaled down to 1. D1 is sigma plus 1 by C1. This whole process keeps on happening till this loop converges or runs out of iterations. We have specified, I think, 30 iterations. We have converged in 4 iterations. You can see that there is D3 is minus 0.02. This is my sigma value. This seems to be my lowest eigenvalue, and this is my corresponding eigenvalue. Just to specify, because we can check it here, I just run A dot eigenvalues, and I can see that there is indeed an eigenvalue which matches to whatever we have evaluated. If I check the eigenvectors for minus 0.02, this is the eigenvector. This is what we have. So both of them are matching, 1 minus 0.83 and 0.21. Okay, so this completes the inverse power method algorithm. Okay, and it works only because our initial guess sigma is equal to 0.01 is much closer to this value than the other two. I think suppose if I take something like 4, I doubt if it would work. It give me this value, which is closer to 7.25. Okay, for the smaller value, this is how we go. Right, minus 0.02635. Okay, so this completes this example. Any doubts here? Okay, next we move on to the example 12, which is the final one for this week. Consider a system of linear equations Ax equal to b, where A is a 3 by 3 matrix given here and b is a 3 by 1 vector. Set up iteration schemes. Schemes. Xk plus 1 is h times xk plus d for Gauss-Jacobi and Gauss-Seidel methods. One thing that I haven't specified here in the problem statement is we'll be also looking at spectral radius of h, which is important in the context of converging of these methods. So the way these methods work is we have already seen in class, but I think I have a recap below. We first specify the matrix A and the vector or the matrix B. Next we specify LD and U matrices. Again, this diagonal matrix L is U is this, and L is strictly lower triangular and U is strictly upper triangular. Next, we do A dot solve right of B. So this should give me a solution, say X, and if I multiply A with X, I expect to get B again. So my X is minus 0.6, and minus 0.2, and if I do A times this X, I get 1310.5, which matches my B matrix. So this is my exact solution. Now how do I get here? Using firstly the Gauss-Jacobi method. In the Gauss-Jacobi method, my iterative matrix H is nothing but minus D inverse into L plus U. So if I write my iterator matrix H and print out its eigenvalues, I see that the eigenvalues are 3.5 minus 0.09 and minus 3.4. Now this is a problem because as we can see, these methods are convergent only if the spectral radius of H is strictly less than 1. So in this case, spectral radius for an n by n matrix is defined as maximum of modulus of lambda of A, where lambda of A is an eigenvalue of A, which means my spectral radius is 3.5 greater than 1. So uh, multiplication with the iteration matrix over and over again will not converge to a proper solution. So that is what I have written, that we do not expect it to converge. Next, we define the Gauss-Jacobi function. This takes inputs arguments as matrix A, right hand side vector B, x0 as my initial guess, and n as my number of iterations. Using this algorithm, I'm basically calculating D, U, and L matrices, then the D inverse LU matrix, D inverse minus of D inverse into L plus U matrix, which is my iteration matrix, and my C matrix, which is D inverse of B. Now I run this loop for my n iterations and basically doing this A times, oh it's not here, xk x n plus 1 k plus 1th x is nothing but h times xk plus c. So what the line is, and I return the final. Once I run the Gauss-Jacobi, suppose my vector is 100 initial guess for 50 iterations, what happens? I get a value which is quite far from what I need based on the inbuilt solver. Similarly, if I do the same 100 for 1000 iterations and 010 for 1000 iterations, both of them give me completely different values. So what this tells me is it's always a good idea to uh, first check what the iteration matrix is and what its spectral radius is. Because spectral radius is greater than 1, specifically 3.5 in our case, this method will not converge. So next we do the same thing for the Gauss-Seidel method, where the iteration matrix is slightly different, minus of L plus D inverse whole into U. Now here in fact the spectral radius has increased to a much larger value, around 10.6. If I run the Gauss-Seidel algorithm, first calculating the UL matrices, then the iteration matrix and constant matrix C, sorry, constant term C, and then calculating X is H times X old plus C. For a chosen 100 matrix, this is what the solution looks like after 100 iterations. After 1000, it has increased in magnitude. If I change my initial guess, again I get different value. So clearly, the spectral radius is an important concept when using iterative solutions for such linear algebraic systems. Right. Suppose I were to tinker around with this and say is minus 0.2, 0.7, 0, 0, 0.5, 0.8, and 0, 1, 0, 0.8. Again, I have some values for LDU. I have to do this. A dot solve rate gives me some value, and I do not have now this Jacobi. Let I use the Gauss Jacobi method. This is what my answer looks like: 20 and 9, e to the power 10. So again, it seems like this random changing of uh, this random changing of uh, my uh, my terms of the A matrix did not lead me to a nice solution. So if I just print h dot eigenvalues here in the algorithm itself, and see that there is a value greater than 1 here. So if I go to the Gauss-Seidel method, again this is not what we have. If I do h dot eigenvalues, print, so again you can see that this is a problem. You won't get the exact solution. Okay, in both cases for both methods with different A's, I still see that the spectral radius exceeds 1, making the entire iterative method quite not useful rather in this case. Which is why, again, before running an iterative loop with spectral, for this iterative methods to solve linear system of linear equations, good idea is to write down your figure out your spectral radius for the iteration matrix and then only proceed. Okay, so any doubts here or any of the examples that we have seen so far? Okay, if not, then I'll close this session. So yeah, thank you for attending, and I'll see you again in the next one.